Hey friends, and welcome to the channel. In today's video, I'm going to be going over two new Allsky builds that I've recently put together. I will show you how to use the software that I built these with. It's a very intuitive software. You can either download it to your computer, run it locally, or you can use my hosted version on my website to put together the build. Basically, you'll see a graphical interface. You'll be able to change different aspects of the design. And once you've got it perfectly suited to your needs, you just hit export STL and you can download the files and print them on your own 3D printer. If you don't have a 3D printer, no problem. Maybe you have a friend that has one, or you can use one of the online 3D printing sites that are available. The software, like I said, is completely free to use. There's no charges for it. We will go over different aspects of how to install it. We go over how to install Indi-Allsky. We'll do a complete build. If you've never done something like this before, you can just follow along with how I'm doing mine. I'll give you step-by-step instructions, and I think you will enjoy this video very much if you're interested in building your own Allsky enclosure. Now, if YouTube just randomly dropped you off on this video, if you have no idea what an Allsky camera does, then watch these videos real quick so you can kind of get an idea of what these things are capable of. So in the first video that I'm showing, this is going to be a daytime time lapse that the Allsky camera captured. You can see the clouds rolling in, kind of a cool effect. But this next video is really cool. It shows the Milky Way high in the sky and a thunderstorm rolling through with the lightning flashing through. And then this last video is a Chinese rocket that flew over the United States and it off-gassed right over the central United States. Kind of a wild video to watch, but we were assured that nobody was affected by the fuel dump that they did, but who knows. Anyway, hopefully you enjoy this video. There are chapters. This video is going to be a longer one that I'm normally putting together. If I'm covering something that you're not interested in, just hover your mouse over the timeline and you can jump to a chapter that may be of more interest to you. So I hope you enjoy it. Thanks for watching. So before we get too far into the actual software, I want to talk about how we got here. When I first built my camera, several friends saw it and they wanted to build one, but they didn't want my ugly model. They wanted the sleek tubes that they had been seeing on some of the printable websites. But of course, several of them wanted to use different cameras. Several wanted to use the PiCam HQ, had a couple that were saving some money for some of the planetary cameras. They would start with the PiCam HQ and then they would upgrade to the planetary cameras later, which kind of complicated things. Knowing if we went with a specific model in mind, they wouldn't be able to use their new cameras later. So we came up with several different cradle designs that would try to accommodate everybody. So we have the ASI 533, we have the planetary cameras, we have player ones, and we have the HQ. So this first model is my 533, and it's a pretty chunky build, but it works perfectly for me. It supports all the different components being strapped to the side. The dew heater attaches just directly on the top. It twists on. The blue O-ring that's on there, it actually sits at the very bottom, and then the actual tall tube will just sit over the cradle and just twist to lock and secures it in. And then of course, going to the other side, we have the standard tube model. This is designed for less components possibly being on the cradle. Maybe you want to run a split system where you have a mini computer inside the house and you just want to run a long USB cable out to the tube, and that works also. Whereas this one, instead of coming in underneath, it stacks in directly from the top down. But that's kind of how we got here, and just wanted to give a brief overview on that, on why we have so many different setups that are available. So to run the design tool locally, you're going to need to download Python. Python is a free scripting language application that it's available for all platforms. Windows, Linux, Mac. We're going to just show a Windows install right now. So make sure when you download it, remember where you're installing it at, and then kick off the installer. Now the important thing is make sure you check the bottom option, add Python to path. If you don't, you try to run it from the command line, it probably won't run, or it'll pop up with the Windows Store and it'll prompt you to install from there. You don't want to do that. This gets kind of messy. So make sure you choose that add path option and then continue. Once it finishes the install, we'll do some sanity checks on it, make sure we got the right version. And you'll see that right now we're downloading 3.14.6. So we want to make sure that when we check our version that it actually matches that one, because you may already have an install of Python on your computer, but you just weren't aware of it. Close to that, we're going to go down and bring up a command prompt. So you can type either command, the word command, or type in CMD, Charles Mary David, hit enter. And at the command prompt, we're going to type in Python -- version. And you see that Python 3.14.6 is what we installed, and that's what we're showing our current version to be. So we're good to go on that. Okay, so we have Python installed. Now we are ready to download the Python scripts that will run our SkyForge software. So to get those, you go to washitaobservatory.com/SkyForge. And I will have a link to this in the description because Washita can be awkward to spell sometimes and don't want you to get bad addresses. So there will be a link to click on in the description. It'll take you to the site if you can't remember what the link was. So hit enter, and then when we have this page, we'll say download SkyForge. You'll be prompted for a location. I'm just going to drop this into temp. So SkyForge, it is a zip file. Now, if you get prompted by your web browser that it's not safe, some web browsers have additional security that may say zip files are not safe. They're safe. They're just compressed files with additional files inside of it. So just choose to keep it if you're prompted. Okay, so we've got it downloaded. We will go ahead and open it. Say SkyForge. And then you'll notice, depending on which zip extractor you're using, you'll see that there's already a folder in there called SkyForge. So if you hit extract, it should drop it, the entire folder, wherever you decide to drop it at. So like on Windows, you may have a C or a D drive. Mac or Linux, you may have different volume names. So we're just going to put this directly into D. No additional folder structure. This folder structure will carry over. So we'll say D:// OK. Okay, the file's been dropped out. Now let's go to our D drive, make sure it's there. Yep, it's there. Okay, so we have all of our assets that are needed to run the script. The main one that we're going to work with is this allsky_GUI.py. These other Pi scripts are basically just the assets that help generate the different components of the model. Now, one thing I will say before you run any Pi script, especially that some stranger on the internet offers you, take these and run these through your favorite AI agent, whether it's Gemini, Claude, ChatGPT, because Python is a very powerful scripting language, and bad guys can do bad things to your computers by just, if you run these on your machine and you really don't know what the contents are. So you just consider these things to be possibly viruses, malware. But I'll assure you mine are clean, but don't take my word for it. Go to Gemini, Claude, or ChatGPT, drop these files into their processes and just ask them, hey, is this file safe? And they will analyze it and tell you, yes, it's completely safe. It's some weird Allsky enclosure generator. So that's what you should get anyway, something along those lines. Not maybe weird, but awesome. Anyway, so we are going to jump out. We've got the files we need. We will jump out to a command prompt. We will change to the SkyForge folder. Okay, one more thing we need to do before we try to launch our SkyForge software. We need to install some dependencies, basically little applications that will be running to help make sure everything looks correct. So at your command prompt, we're going to be in the folder where you extracted it to. We're going to type in pip install -r, and we're going to type requirements.txt. Now, the requirements.txt basically just tells the Python application what modules do we need to have pre-installed, and you only have to do this one time. So you'll run the command pip space install space -r space requirements.txt. You'll hit enter. Okay, so now that part is done, and we'll move on to the next step. And now here's where we will run our Python command. So we're going to type Python, and we're going to type allsky_GUI.py, GUI.py. Okay, hit enter, and this will launch the SkyForge interface, and you will get a disclaimer, just basically me telling you that the software is provided as is, and I don't guarantee any of it, but I have to do that because legal reasons. So I accept. All right, so now we will explore the interface. Okay, so we're in the interface, and one thing I forgot to mention, when you run the SkyForge command, you will get this message that it actually shows the application running. Do not close this window because this is your local web server that's running that supports the SkyForge interface. So if you close this window, then next time you click on any of the options in the screen, you'll get an error message. So make sure you leave this running. Now, one thing to notice on here, this is running on your local host address, which is your 127.0.0.1 port 5000. If you already have something running on port 5000, I guess just message me and we'll have to figure out another way for you to run it. But most people don't have anything running on port 5000 already. That's why I chose that as kind of a safe port. So let's look at this interface. Whenever you're moving around on this interface, you have different options. So you have your tube system, you have standard or tall. So depending on if you click the standard option, you get all the standard tube accessories. If you click tall, you'll notice these change. These are all the taller accessories. You have the option to generate the STL. Once you choose your option, it'll pop up over here. You have the option to reset any of these parameters down here. If you change something, you're like, messed it all up. Let me just start over. Just hit reset params. And then finally, you have the option to download individual models. So if you generate, let's generate this head cap. We'll say generate, and then I just want to download it. So we'll hit download, and then you see you can pop it into your whatever folder you want to save it to. Let's see, if we adjust some of these parameters down here, cap outer radius, that's basically the thickness of the cap. It's not going to adjust the threads, it's just going to adjust this part. Cap skirt, say you want it to be longer, you don't like where the holes are at in the neck of the tube, and you want the cap to be longer, you can adjust that. Just get around there and play with it. Just be careful on adjusting too many settings because you can wind up with something that may not be completely compatible. Let's look at the interface. If we're looking at this, you have ways to move these things around. If you left click, it basically it's kind of a free view. You just click around, drag. You're just holding the left mouse button up and down. I'm dragging all over. You can see how I'm just moving my mouse around. If you want to pan, basically you just right click. I'm right clicking the mouse and this is just a pan left and right. If you want to zoom in, just scroll your mouse wheel or hold your mouse wheel, the middle mouse button, and then drag forward and back. So we're doing that. Now the slow zoom in is just to roll your mouse wheel. If you have a mouse middle button that's a wheel, just scroll back and forth like that. There are some quick views up here. You have an isometric view, just puts you up at an angle looking down. You have a front view, which on this cap, it's going to look like, everything's going to look like a front view because there's no real shape to it. Top view, we'll move that back and forth, pan it up, and the side view, of course, that looks like the front view because it's round. So the other thing that you may find interesting is this wireframe view. This allows you to see into it, so you can see through the polys on here. You can kind of zoom in, you can see where the threads actually start on the cap. If this is useful, especially if you've gone into the model view where you can see how the things connect together. Of course, the model view does do a transparency on the different components. And we'll jump into that in just a little bit. So, see the underside, see where the threads are. And one thing to notice, you'll see these threads, there's multiple starting points on these threads, so that gives you the option to have a quicker tightening. A 27-degree turn completely tightens this lid down. So you have a thread start there, there's another one there, where some screws you have one single start thread. This has 3 different levels where it can start at, so it just allows you to start tightening things faster. Okay, so back to the overall design. Let's look at some things that you can do with this. If we go to the standard view, we've already got a head cap, and it's got a dome, transparent dome that we already have on there. This is just for visual purposes. Obviously, it's not going to print the dome for you. You have to buy that on Amazon, and I do have the part that this is modeled around. But you can also use a different dome. If the dome has a different diameter, you can actually change the dome seat on here, the dome hole radius. So you can actually change that. If we change that to say, let's do some crazy number, let's make it a really small dome. We'll say 32, and we'll say generate the STL, and then there's your smaller dome. So you could, or dome hole radius, and then you could put a smaller dome on that. And then you have your smaller dome seat radius where you could bring that in. So this is the dome seat right here. So obviously we've extended past that. We need to bring that in. We'll say that dome seat radius will be 35. And you'll notice up here, if you type in a value that's not compatible, it'll tell you you can't do a 3mm dome seat. That would just not fit. So we'll do a 35. Hit generate STL. And now you see your dome seat fits right onto the edge of that. I know there's multiple sizes of domes that you can get for these things, so I'll try to make it compatible with everybody. All right, so let's reset this because we're just going to model this as a standard configuration. So reset the params, generate the STL again. We're back to defaults. Now we like that dome, we'll add it to our model. So we've got our head cap in our model, and I'll show you what this does in a little bit so things will make more sense. Now let's go to our head tube. So this is a standard head tube. It's not the tall one that you saw earlier in the video. We'll say generate the STL. And these tubes do take a little bit longer to generate, depending on how fast your machine is. If you've got the power of an Etch-a-Sketch, it's going to take quite a while. If you've got a supercomputer, probably not going to take very long at all. So this is our standard tube. You'll notice we have the vent holes, which you will want to put screen on the inside of these so that bugs can't get in. And then also on the bottom, this bottom ring, just the outside. And there are templates that will be included in some of the zip files for the actual STLs, for the default builds, that you can print out so that you have a template to cut your screen with. So those are included. It just makes it a little bit easier to have a kind of a donut ring that you can cut your screen around those and be able to drop it in and glue it so that keep the bugs out. And then inner side of the vent rings here. So everything looks good on that. We are going to add that to our model. So now we have a head tube, a head cap. Now we got to choose our cradle. So a lot of people will probably be either running in the Raspberry Pi high quality cam or the ASI 676, one of the puck models, the kind of the planetary models. So we're just going to go ahead and choose that one. We'll say we could generate the STL, but what we really want to do first is we want to put a lens on here, because when it generates the STL, it's going to put a mock-up of what the planetary camera looks like, and we need to try to put a lens on there so we can see how high it sits under the dome. So whichever lens you're going to use, try to get the specs on it, basically how tall it is from the seat of where it screws into the planetary camera. Most of them I've seen are around anywhere from 25 to 35 millimeters. So we'll just do somewhere in the middle. We'll say 30 millimeter lens length from the mount on the camera. And then we'll hit generate STL. Okay, so here's our imaginary planetary camera, and here's our little lens that we chose. We did a 30 millimeter lens on that. Now we will add that to our model. So we have these three components. One last thing that you do want to include on here, you want to get your dew ring on here, because the dew ring kind of sits a little bit above this threaded ridge right here. So we'll go back on here, make sure you grab the dew ring that's for your model. Obviously, we don't want to grab the ASI 533 dew ring because it's a pretty tall dew ring. That's a full-size astro camera. We'll grab the dew ring tray, generate STL, and there's our dew ring tray. And you'll notice on here we have the holes, like I said earlier in the video. You can do a DIY resistor on here, like for or whatever ohm that you set, or you can just buy one. I think dew control is a pretty popular dew ring, and you can buy one of those and just not have to worry about using the soldering iron. So we've got that set up. Now we're going to add that to the model. Now we have all these options on here. This is basically a full setup. Now what this is for is to give us a view to see how high the camera is sitting inside the dome. There's usually two camps that I see with people that build all-sky cameras. Some say make sure the camera reaches all the way to the top of the dome. Some people say let it sit just above the ridge of where the dome is. And I sit right in the middle, and I don't have any reflection problems, but I'm also in a dark sky area, so I don't have to worry about street lights coming in the side and casting a reflection. But let's go ahead and model it. So now here's all of our components stacked inside of your all-sky enclosure. So you can see kind of where our camera is sitting at. Our lens is sitting about halfway. You could actually increase that on your cradle. Say you're not happy with it sitting down this low, or maybe it's sitting too high for you. Maybe you're the camp that wants everything to be sitting down real low. You can adjust this cradle on here. You can basically just go back to your cradle, and then we'll generate it, and it'll replace this. We can go back and model it in a second. Okay, and you'll get some messages on here basically telling you different parameters of how high certain things sit, where the camera sits at, things like that. But what we're interested in is we want to raise that seat. So that camera, you can use the plus to raise it, negative to lower it, and that's basically pushing this part up. So if we say, I want that camera to almost touch the top of the dome. Let's say, let's raise it up by 20 millimeters. And then we will go down, make sure there's no other parameters, everything's good on that. Generate the STL, okay? And now it's been raised up. So now let's add that to the model, and it will automatically replace the existing model that you have in there. You don't have to worry about closing it, clearing it out, and then adding the new one. So just hit add to model. See that flash green, it threw it in there. We'll hit model it. Now we are very close. Also keep in mind when you're doing this, your dew tray is raising up too. So make sure that you've considered that, because otherwise when you build your cap with your dome on it, this dew tray may actually touch the edges. And I may work on a solution around that, but it's kind of the whole thing is just moving up there. Maybe the solution is just to get a taller lens. Wish it was that easy. Anyway, so that's how that works. Oh, and for reference for size, if you're trying to target a certain size, these domes, these enclosures can be made shorter. Basically, I'm building it around my 533 design, where I have a very tall camera, and the rest of the world uses those too, in my imagination. So everybody gets a tall enclosure. Not everybody probably wants a tall enclosure, but you can reduce that. So if you want to go back into your cradle and you want to take off a few inches, millimeters, whatever, you can do that. Just make sure if you change the enclosure height, you also change the cradle height. But you would see that when you modeled it, that the enclosure was, or the cradle was sticking outside the enclosure. But if you want to see the scale for it, just throw yay, add a soda can, and that's basically the height that you're going to see. Now on the standard view, it's not that big, but on the tall one, it's a pretty chunky enclosure, and I have no issues with that. I'm proud of that big boy. Anyway, we'll show that one in just a little bit. So that's pretty much how you do all this. Now, if you want to export the PNG of this view, you can do that. It'll take a snapshot. But if you're ready to save the STL files, go ahead and hit Save STLs and Photos. It's going to take a couple snapshots for you, so it'll save those as a file, and it'll save all your parameters that you did. This way, if you go back and you want to rebuild this exact same thing tomorrow and you've already closed out your browser window, you can just re-input all those parameters. So we'll put this in here, Terrible Designs, that sounds appropriate. And we'll pop that open, and then here's all your images. Here's your specs. So if you wanted to see what each one of these were, just double click your specs. Yeah, Photoshop, I know I'm paying the tax. All right, so Washita SkyForge, here's your design tube. This is all the parameters that you had. And basically that just kind of shows you everything that you configured on that build. Your views, if you want to see each one that it took a picture of, you can pop those open. But you can just extract this zip file to your folder wherever you're going to be printing it from. So, and that is that. Here's the tall build. We'll go to the tube tall. I'll just give you an example of how big this one is. But this does fit my 533 perfectly, and that's why it's this tall. So let's clear all those out. We don't want those in there. And if you try to leave those in there, you try to model it. Obviously, you can't use a short cradle or a standard cradle inside the tall tube. You have to do a tall cradle in the tall tube, and it should give you an error message. So anyway, we will add this to the model, and then let's say model it, and you see the height on it. It's about twice the height of a soda can. Other options that you do have on here is we could engrave your cardinal points on there. This is more of a novel idea, because sometimes when you get your camera inside there, they may not exactly line up with the northeast southwest. If you're lucky, they might, but I put it on there thinking I was going to be able to do it, and it didn't always work out for me. It really depends on how tight you get this on there. If you can adjust your camera inside the body to be true north. With the puck camera, since the USB connection is on the side, there is room for you to adjust it. But on the 533, the connections come in through the bottom. So there's kind of a template where I've got cut on the cradles. We'll just generate one real quick so you can see what I'm talking about. Okay, so on here you see these little holes cut out. These are basically like the fan of the 533, the power port, the USB connections. You're locked in, basically your camera's going to be sitting in this direction, and if these threads tighten up early before you're able to rotate your top of your sensor to north, then you may not be looking at exactly north. Anyway, that was just a little caveat to that. Let's see, go back to the head. And also, one other thing I forgot to point out was on the tube, depending on what you select on here, these parameters change. So if your tube length If you choose tube, you're going to get tube length. If you choose cradle, you're going to get different parameters on that, raise and lower the camera. And so this way you don't get confused on different settings. And I just actually thought about something as I'm seeing these drinks. Does anybody remember Jolt Cola from way back in the day? Remember, God, I'm aging myself now, but this is probably back in the early 90s when we used to do LAN parties, QuakeCon, stuff like that. That Jolt Cola was, I think their tagline was like, all the sugar and twice the caffeine or something. God, that stuff, you would drink a can of that, you'd just be shaking. It was maddening. How probably shouldn't have been drinking that as kids, but anyway, I digress. Okay, so now we are going to look at how to run SkyForge from my web server. If you're in a situation where you do not want to install Python, you don't understand how to install it, you don't feel comfortable doing it, that's perfectly fine. That's understandable. Running it from my website will be much, much slower because I have to put resource limiters on these hosting providers that I use, because if somebody got into this app and tried to generate 10,000 SkyForge enclosures just to be malicious, they could run up a significant web hosting bill for me at the end of the month. So I do have to put limits on the resources that are used. But to go to that server, you will go to SkyForge, forge.ouachitaobservatory.com, hit enter. You'll get the same prompt about our standard legal disclaimer. The interface looks identical. You'll probably not notice anything different from running it locally. Remember your 127.0.0.1, that's your local host running on your local computer. Now you're running on my servers. So the biggest thing you will notice is the speed. This server is not going to be fast, and that's by design. So we'll jump on our standard head cap. The smaller STLs generate pretty quick. So if we hit generate STL on this, it'll pop up pretty quick. Yeah, no problem on that. Where you will see the lag will be on the more intensive models like the head tube. It doesn't seem like it's that much more complicated, but there are a lot more polys that it has to generate when it's doing the STL. So it will hit head tube, generate STL, and we'll just watch this timer. I think earlier we were getting maybe 5-10 second generation times, but now we will feel the pain, and this is limited to a certain number of people generating their files at a time. I don't expect this to be a super popular application, but when I first release it, if 10 people are on the server trying to use it, there's going to be a queue. It will allow 10 people to sit on the server, but only 2 people can model at a time. So as soon as they click submit, then if you've already clicked submit, yours will be next in line. So, okay, so that took a total of, and this will show you how long it took, 45 seconds. So that was quite a bit of difference as far as doing it locally versus on my hosted server. But again, it works completely the same. You can still spin everything around. You have the option to save your STLs and photos after you do your model on it. We'll go ahead and we'll switch over to the tall, generate the tube tall, and I'll speed this up so you don't have to sit through it. Okay, wasn't too bad, only 17.5 seconds. Interesting, this is a taller model, but still finished faster than the smaller one, but either way, felt like I was sitting on the phone with a DMV. So we'll go ahead and add this to our model, and then we'll do a cap, generate the STL, add to the model, and then we'll just do the 533, my special camera. You got to hit generate STL first. Okay, forgot to put a lens on that one, but that's all right. Add to model. And we have all that. Just say Coke can and model it. And then, yeah, you'll see the 533 is a very tall camera compared to some of the pucks. So that's why the dew tray, the dew ring that you have on here has to be a different size. It can't be the standard one that comes with those. Yeah, much taller. And then we'll add that to the model. And then we'll model it. There we go. And then save as the STL. Okay, and then you'll be prompted. Save that as a separate build. That's the tall build. Save. All right, and that is pretty much it on that. I don't know if really anything we need to cover other than maybe some of the parameters. If we need to change something, let's say on the dew tray, we can raise the dew tray towards the dome. Really shouldn't really have a need for that, but it's there if you need it. If you want to make just a crazy tall one, you could say raise it by 75. Of course, that dew tray would never fit inside where the glass dome is, but it just shows you it's capable. But again, if you do ever make changes to all this, even though you're using the modeling tool, hit the wrong one. You can see when I add it to the model how that pretty much extended past the glass. So these are the kind of things you have to be careful with whenever you're making parameter changes. You can make a system that's not really compatible with it, and my tools won't really check for those type of things, because maybe you do have a dome that is really tall. Maybe it goes way up there like that. Of course, you'd probably get some really weird distortion in the glass, but we can't really check for every possible scenario of how you could build your components. So if you do end up making parameter changes, you can model it and take a look at it and make sure that everything looks like it should. But at the same time, definitely drop this into whatever your favorite CAD program is, and just make sure that every component lines up correctly like you expect it to. My modeling is really just best effort. There's no way I could possibly check for specific heights of a specific lens. If you had your lens height incorrectly, maybe you are touching the glass, maybe you're sitting below the rim, and you will not get that 180-degree view without obstructions on the side. Definitely export these STLs out, put it into your own CAD modeling program. I think Tinkercad's pretty popular. There's several CAD programs that you can drop these into and basically build it and make sure that everything is exactly how it needs to be before you print it. Because I'll tell you, these tubes, I'm printing mine in ASA and making a pretty robust shell on it, and it's taking upwards of a little over a day just for the tube alone. So you will definitely have some time spent with these things, and there's nothing worse than printing it out and then finding out you did something wrong, and yeah, you have to start over. So the whole thing measure 4 times and cut once, it kind of applies to this too. All right, so that wraps up the actual modeling application. If you do have any questions, you can always go to my website, ouachitaobservatory.com, and hit the contact us. Or I'll have this video on YouTube also, so you can comment there if you've hit like a obstacle. You can just definitely drop a question, that you drop whatever questions you have there, and we will be able to respond to you hopefully pretty quickly to answer any questions that may come up. If you find a bug, try to give me as much detail about the bug. Don't just say it doesn't work. Tell me what doesn't work and what process you went through. Because if you just tell me it doesn't work, I'm like, okay, cool. I've got 25 people that have already used this already, and we know it works, but there's always a chance for a bug. There's always something that we may have missed. But definitely give me exact detailed steps as far as what you were experiencing and how you created the bug, because we'll need to reproduce that bug. All right, so I think that's it. We'll move on to our next step, and that's going to be the assembly. So we'll be assembling my ASI 533 model. So for those of you that don't really feel comfortable wiring, you can watch that part of the video and see how we do this. And this is all low voltage. Shouldn't be at too much risk. It'll be fun. So if you're not interested in that part, move your mouse along the chapter bar and see if there's anything else I have that I'm covering that you might be interested in. Now, if you don't already have a Raspberry Pi purchased, you can look at Amazon or whatever shopping site you use. Just do a quick search for Raspberry Pi 5 4 gig, and we only want the board. We don't want a case or anything like that, because the case will not be installed inside the enclosure. There's just not enough space for it. Now, you have 2 options when you're looking at the Raspberry Pis. You have a Raspberry Pi 4, and this is the 4 gig model, and the Raspberry Pi 5 with the 4 gig model. And I wouldn't recommend going less than 4 gig, especially if you plan on using all of the features in the Indi-Allsky software. It just requires a little bit more resources to do the time lapses, do the keyograms, kind of the housekeeping type things. You want to give it enough room to move around. And if you go with a 2 gig model, you're going to start constraining the resources on it while it's trying to do multiple processes simultaneously. Now, with that said, the Raspberry Pi 4, the Model B here that we have here, 4 gig, it's about $120. Now, the Raspberry Pi 5, 4 gigabyte, see our options and see all buying options. What do we have here? Okay, so for $8 more, you're getting a much more capable processor and version of the Raspberry Pi. So I would highly recommend looking at the Pi 5 4 gig for $128. You may be able to find some other Raspberry Pi 4s, maybe much cheaper, but make sure you look at the memory that's on it. If it's a 2 gig model, you're probably going to starve your system for resources. So definitely no lower than 4 gig. You don't need to go with a 16 gig model. Your benefit's not going to be there for what the price is going to be. So just try to stay in the 4 gig range and you'll do well with that. Now with the system, it's the board only. It does not include an SD card. You'll probably want to look at, depending on how much data you're trying to capture, you may want to look at an NVMe drive with storage on it. NVMe drives are just, they're more write robust intensive, whereas an SD card, it does have a life expectancy after however many years it's been out working. So you definitely want to look at those two options. If you just want to start out basic, definitely just get you a 64 gig SD card and pop it in and you'll be fine for a while. But if you're looking at this being out there for years, and if you want to keep quite a history of your images and time lapses and things like that, then you'll want a much more robust NVMe drive that can mount. Basically, they have little hats that sit on here and it kind of just extends off the system. One other thing that you will want to get is when you get the board only, you need to look at a fan, because this board does not come with a fan as far as I know. I don't see any option. I did not see a fan included, but if you just get a Raspberry Pi 5 fan, I think it's about $10. Let's see here. They actually do have a manufacturer model that they will offer. This one right here, exactly. This is the official active cooler for Raspberry Pi 5. There's holes already on the board where these little punch through connectors will connect to the system with. This little cable, there's a pin out on the board that you'll plug this into that provides power to the fan. And it basically just turns the fan on and off as it needs to cool the processor down. And these enclosures do get warm, so you don't want to pop a Pi in there and have it start heating up, because it will throttle itself and it could even shut down if the heat is too high. All right, so with that stated, and if you have not chose your board, if you have not ordered it yet, those are the two that you'll want to look at. So now let's jump over and see how we can install the software. Okay, so with this, we will choose software, and we need the Raspberry Pi imager. So that's what we have here. Download for Windows. I'm running on a Windows box right now. They do have Mac OS and Linux distros that you can download for those operating systems. So we'll just go ahead and choose download for Windows, and we'll drop this into, let's see, the software folder here. Yeah, let's drop into our software. Okay, so here's our imager. It's already downloaded. Now we'll click on this. Now, if you're prompted, if you don't run Elevated or as an administrator on your machine, you'll be prompted for your password, which it's doing on mine right now. And then we will see OK. And basically what you want to do at this point, you'll have your SD card already inside a card reader attached to your computer. So when the Raspberry Pi imager setup wizard starts, it's going to be looking, the next steps will be looking for where are we going to write this image to. Obviously, we don't want to write it to our hard drive, and it would probably fail on that. I'd never actually tried that, but you need to make sure you have an SD card already discovered by your system and available for the process to write to. So we'll choose Next and accept the agreement. And we don't need an additional desktop shortcut. So let it finish the install. It's going to prompt you, do you want to install this additional software? Since we're not going to be using this Pi as a gadget or anything like that where we're attaching it to our computer, we're going to say don't install. We do not need that particular driver installed. Okay, now we will launch the Raspberry Pi imager. Now when it comes up, you need to already have decided which device that you're going to install on. So if you picked a Raspberry Pi 4, you'll choose the Raspberry Pi 4. If you choose a Pi 5, then that's the option you'll select there. So we'll choose that. Next. Now which OS do you want? Indi-Allsky does support the latest Trixie version, so you want to choose that top option. 64-bit Trixie. And in storage, right now it's detecting the SD card that I have in my card reader. It's only a 32 gig SD card, but that's fine for what we're doing on this. Is 32 gig is sufficient. If this is something that you're going to have in your system for, you plan on having it for years, you'll probably want maybe 128 or 256 gig just to be able to accommodate the amount of images that will be written. Choose that drive. We're confirming that's where we want to install it. Okay, so what is the name of your host system? This is an old build that's detected, so we're just going to call this Allsky, and then we can hit next, and then what's your location? Choose whatever capital city that you live near. All right, next. Now this is where you want to put in the login information, because you're customizing the actual build information that when we take this SD card out of our writer, we're going to put it into our Raspberry Pi 5, and when it boots, it's going to read this information off the card, and it's going to set up the operating system with these parameters that we're specifying now. So it's important that whatever information you provide here, that you remember what it is, because when you go to log into it later, it's going to expect you to know this. So I'm just going to type in Allsky as the username, and we're going to do an incredibly insecure password. We're just going to type in password. Obviously, you want to have good security hygiene and use random passwords. Don't reuse the same ones. But if it's on the inside of your network, yeah, you can get by with using a weaker password. But Allsky, and our password is the word password. Confirm that you've actually typed in what you think you did. Those two are correct. All right, and we'll hit next. This is where you're going to set up the Wi-Fi. Go ahead and enter whatever the network name is. So the SSID, on mine, it's Farm at Woods Edge. And then a password, you want to make sure that you enter the correct password, because like I said, these are parameters that are written to the SD card. So when you pop this into your Raspberry Pi, it's going to read all this information as part of the setup. If you get your Wi-Fi password wrong, your Raspberry Pi is not going to be able to connect to your Wi-Fi network. There's other ways to get around that. You could attach your Raspberry Pi directly to your switch and let it get a DHCP address like that, but less convenient. So you will go ahead and put in your information, and then you'll hit next. Okay, so we have our information in. We have our SSID and our password. We'll click next. Okay, you do want to enable SSH. SSH is basically a way to remotely connect to the Raspberry Pi during our setup. So make sure this is toggled. And then you do want to use a password authentication. We won't get into the public key authentication. That's kind of outside the scope of this video, but for now, we're just going to use the user password and authentication on that. That's the Allsky username and the password, the word password that we set up earlier. Next, we're not going to enable the Raspberry Pi Connect. We don't need that right now. You can always do this later. Okay, and now it's ready to start the writing of the SD card. We'll hit write. You're about to do this, and if there's anything on that card, it's going to wipe it off and rewrite this new data on there. So make sure this isn't, your SD card doesn't have family photos and stuff that's very important to you. Preferably just make sure it's a new card. You won't have to worry about that. Okay, it's finished writing. Now it's going to verify that the write was successful. Okay, the Raspberry Pi has finished writing. You can see it says write complete. You would look through here, make sure there's no error messages. For the most part, it's a pretty straightforward process. There's rarely any issues that I have whenever I'm writing using the writing software to do this. So we'll hit finish, and then we will remove the SD card from the writer, and we will take it into the other room, and we will pop it into the Raspberry Pi and make sure it boots up. Okay, we're ready to take a look at our Raspberry Pi 5 board. Now, if you've never seen or worked with any of the Pi computers, you'll notice the first thing is they're very small. Small but capable. One thing you definitely want to make sure is that you hold it by the edges. You do not want to grab it on the face or the back, because you have a printed circuit board on the back and you don't want to short it out. So definitely, while you're holding it, make sure that you're gripping it by the corners. You do not want to static discharge and ruin your device. So, taking a look at the ports that we have here. The very first port is a USB-C power port. You have two HDMI ports. The first HDMI port closest to the USB-C is your monitor output. So, and if you had a monitor like I was just showing on the background, that's something you could hook up to that port for troubleshooting purposes, things like that. Of course, you'd need an adapter that connected to it, which will be a micro HDMI to whatever HDMI input you have on your other side. Now, these little ribbon connectors, this is where your Pi Cam HQ with a ribbon connector would slide into. Basically, the ribbon would fit down into the slot, and you would push the little tab down to lock it into place to keep the ribbon from disconnecting. And this little white port, this is your power port for the onboard fan. Row of pins is your I/O ports. This allows you to control different sensors like humidity, temperature. You could also control on-off switches for different fans, things like that. And then on the end, we have an RJ45, your standard network cable connection. And then we have several USB ports. You have USB 3.0 and the 2.0. On the back side, we have our SD card reader. Now on the back of the SD card, you have gold contacts. Those need to face down so that they're actually facing towards the board. Make sure it's snug whenever you push it all the way in. Ideally, you will use a power adapter that has a USB-C connection, because that's going to be a more modern power supply, and it should provide sufficient output to power your Raspberry Pi 5. I think the Pi 5 has a 5 amp output requirement. I'm going to go ahead and plug this into my power supply off screen here, and then we'll hook up our USB-C cables and power this thing up. Now, when we plug this thing up, one thing we're going to be looking for is this little LED. This will flash red when it first boots, and then it will go green. And then after a few seconds, you should start seeing the green light flash. As long as you see that, you know the device is booting up correctly. If you get a red-green flash alternating, then you got a problem and troubleshoot further. But for the most part, as long as you wrote the image, you didn't get any error messages, you should not have any problems with this boot process. And we'll turn this light off so that we can actually see this light on here just a little bit better. All right, so there we go. Yeah. Okay, so now you see the light flashing. This is typical of our back in the day when we had computers that actually had hard drive activity indicators where it's flashing, you know it's working. So this is telling you that it's reading the SD card, it's going through its boot process and getting ready to be in a state where you can connect to it remotely. So we'll go ahead and put the board down, and we'll go back to our workstation and we'll log into it remotely. Okay, we're back at our workstation now, and we're ready to check for the Raspberry Pi network connectivity. What you can do is, if you'll recall what you entered as your host name whenever you were writing the image for the Raspberry Pi, on this one that we're setting up now, we called it Allsky. So you can type in at your command prompt, type in ping and the host name Allsky, and you should get a response. As long as you get a return, then you know the device is on the network. I'll give you a scenario. If something wasn't correct, we'll just type in the host name incorrectly. We'll say Allsky1. Now, if we hit Allsky1 when we're pinging it, we'll get it could not find the Allsky host. It couldn't find anything to ping. That's an error message saying it could not find it on the network. So if you get a situation like that, you'll need to troubleshoot your Allsky or your Raspberry Pi and just verify that it did in fact it did connect to your Wi-Fi network, and it did actually get an IP address, or troubleshoot and try to find out what else may have happened on that. It may be something as simple as just rebooting the device, or you may actually need to go in and verify that the device did connect to the wireless network. And we can do a quick troubleshooting trip on that right now. Okay, now we're at the troubleshooting phase of this chapter. If you did not have any problems getting your Raspberry Pi set up, then just skip this part and move on to the Allsky configuration. But if you did have issues, then you're in the right spot, because we'll go through some troubleshooting steps. So the first thing to do is log into your router, your local router, your Wi-Fi router, and see if you have a DHCP lease tab or a section for DHCP leases. Sometimes in there, you may be able to browse the different host names and see if something showed up in there. You'll remember in our scenario, we used the host name of Allsky. Maybe you use that same name, and maybe it is showing up on the list. If it is, great, grab the IP address. You'll be able to communicate with the device more than likely, but you still need to troubleshoot why your own computer is not able to resolve the host name. But if nothing is showing up in there and it's making sense on how to troubleshoot it from that side, then you need to come to the physical device, and that's where we're at now. We're back at the workbench, and the tools you need to use to troubleshoot are a keyboard and mouse. So this is a all-in-one keyboard mouse. I've got a Bluetooth transmitter connected to the USB port, and then we have this monitor that's sitting right below this, and it's just an HDMI connection on the monitor. You have an HDMI output on the Raspberry Pi. You just have to make sure you have the right connectors, because so the Raspberry Pi HDMI port, it's a micro HDMI. So we will go ahead and connect the micro HDMI port, and then make sure you have the connector facing the correct direction. Push that in. And then you see the monitor just lit up behind it. So a couple things we'll look at here. And I'll turn off this light so there's no glare on it. All right, so first thing we want to look at is, do we in fact have Wi-Fi connectivity? So on this scenario, if you did have Wi-Fi connectivity, awesome. You're already one step ahead. We just need to figure out why you're not resolving the host name. This, when you hover your mouse over it, you see it has the network name. We have our farm woods edge, and then we have the IP address. So 192.168.1.102. Hopefully that's showing up on the screen. But in the event that did not have a network connected to it, if this had 2 lines, and I'll show you what that looks like. We'll turn off the wireless LAN. If it looks something like this, then that means your Wi-Fi did not get connected at all. It may even be grayed out. It may not just say have the red line through it. It may just be grayed out. So with that, we will just click on that, turn on wireless LAN, or if the wireless LAN is in fact on but you're not connected, then you would see a list of wireless networks. Go ahead and click on your wireless network name, type in your password, and it should connect. Now, if you're at a command prompt, you can bring up a terminal window and you can type, if you're at a command prompt, you didn't have a GUI running, you could just type in ifconfig, hit enter. And on this, we're going to scroll up to look and see what IP address was assigned. We have on here ETH0, Ethernet 0. This is the physical LAN port. This is the one that a cable would actually plug into. We're not using that, so we'll skip on down to the next one. And now we have our WLAN 0. This is a wireless LAN, so 192.168.1.102. That was what we saw in the graphical interface version of it, so we know that part's fine. Again, if you're only working from a terminal and you don't have a way to get into the GUI, the way to get into that is you will type in sudo raspi -config, hit enter. And this basically just gives you a little menu to work through. So all your network settings are going to be inside the system options. The one we're selected on now, option 1. We'll hit enter. And again, the wireless LAN is the very first option. So we'll hit enter on that. Now at this point, you would type in your SSID, that's your wireless name. Mine would be Farm at Woods Edge. I would type that in and I would hit OK. And then it would go to what's your password for that. And you would type in your wireless password and then hit OK again. And it would try to connect. And if you typed in everything correctly, it should connect right away. If you didn't, you'll have to do some additional troubleshooting steps that are outside the scope of what I can really cover in this video without making this a 2 or 3 hour video. Go ahead and cancel out of this. But those are some of the troubleshooting things that you'll want to do in the event that you did not get the ability to ping the host name. But if you do have the IP address, you're not dead in the water. At the very least, you can still continue, but you'll need to troubleshoot why you're not able to get to the host name, because that can come up to problems later, especially if you're not using DHCP reservations. If you're using DHCP, that means your IP address could change periodically. And if you don't have a host name where the router is automatically associating that host name with the IP address, a month from now, you may try to connect to your Allsky by IP address. And if it's changed, you're not going to be able to connect to it. That's why the host names are always the most reliable route to go. And on top of that, a DHCP reservation, in addition to the host name. This means it will use a DHCP server to assign the IP address, but it will always automatically give you that IP address every single time. It's almost like a static IP address, but not having to keep a spreadsheet to keep track of all your static IPs. Okay, we are now at a point where we are ready to connect to the Allsky Raspberry Pi. So in order to connect to it remotely, you'll use a program called Secure Shell. And the way you access that program is you'll just fire up a command prompt. We'll type in SSH, and then the format that how you connect to the username Allsky at, and then a host name, which is also Allsky. So on my setup, if you'll recall, when it asked me for the user that I wanted to use, I chose Allsky, and the host name we set up was also called Allsky. So it's Allsky at Allsky. If you used any other format for the name and the host name, you would use whatever username you created at whatever host name you created. So my example will follow through with that. It's Allsky at Allsky, and we'll hit enter. And then basically what this is telling you is you've never really connected to this machine before, and this is the fingerprint that it's offering for security. Basically, do you trust this? And on this, since we do trust it, we know it's the machine in the next room. We're going to say yes. We'll hit enter, and you won't be prompted for that again. Enter yes on that. It's pretty much saved to a file that retains the fingerprint. And then, of course, we need to type in our password, which we use that super secure password of password. And then as you type your password, it's not going to echo to the screen, little stars or anything like that. It basically just goes into the void. But as long as you typed it in correctly, you can hit enter. And we did, so it's letting us into the system. Now, in order to start the install, there's a website that you can go to where the developer has provided step-by-step install instructions, and I'll provide a link to that below. And basically, if you just want to follow his script, I'm going to be following it exactly. I'll just copy and paste the commands that he's put on there. He has all the individual steps. You can go to that link and just follow the steps as I'm doing them here. So the first thing he has on his setup is to set up your locales. And you don't have to actually do that one. That's completely optional, and I am actually going to skip that one. So I'm going to skip to step number 2. So the first thing we want to do is we want to do a sudo apt-get update. So I'm copying off his page, pasting it here, sudo apt-get and an update. And this is verifying that we have all the latest info from the Raspberry Pi servers. Basically things that we need to get updated on the machine. And depending on the speed of your internet connection, you'll probably be much faster than mine. I'm on a relatively slow Starlink connection out here in the sticks. Okay, so that part's finished. We'll go up our next command, and it is sudo apt-get install git. Now git is a program that basically handles software repositories. So what this is doing, we're basically ensuring that we have the git program available so we can clone the software over to our machine. So we'll run this sudo apt-get install git. We probably already have it installed, as most Linux distros already do. So it's basically telling us we're good to go. We don't need any updates on that. If you did have an update, it would have updated at that point. Now we are going to clone his repository. So we will copy the next command, paste it in. We're saying git clone, and we're cloning his entire software repository for the install. So copy paste that, hit enter, and you'll see it copying a whole bunch of files, and this will take a little while. Okay, so that part's finished. We've got the repository cloned over to our machine. So now we are going to change to the Indi-Allsky directory. So if we type in cd space and we hit Indi, we type in Indi, and if you press tab, it'll autocomplete because that's going to be the only Indi-Allsky folder that we have. So it autocompletes as you hit tab after you type part of the name. Hit enter, and now you're ready to start the setup process. So to start the setup script, we will hit /setup.sh. So it's going to be ./setup.sh. We hit enter, and we'll have a little menu option to continue. These are all the settings it's going to use by default. Say OK, and then it gives you a 10-second opportunity to break out if you don't want to continue. So otherwise, just wait the 10 seconds and you'll continue with the menus. Okay, so now this is where we're going to select the camera that we've currently got installed. One thing I can show you, and I'll show you in just a moment, how to verify if the camera is actually installed. You could actually do it prior to running the setup script. But on this particular setup, I've got a PiCam HQ that's connected to the Raspberry Pi. So we're going to choose this one. Basically, we just kind of use our arrow keys to move to the camera system that we want to install. I'm going to use live camera. So I've got it selected, and I hit the space bar. That puts a star in there. That actually selects the camera system that we're using here. I'll tab over to OK. We'll say OK. Now the PiCam HQ is an IMX 477, so that's selected at the very first option. Hit space to put a star to confirm your selection. Hit OK. And let's see, do you want to upgrade all your system packages to the latest versions? We can say yes. We probably already did that with the previous updates, but we will go ahead and say yes to that just to make sure that we are running the latest builds of everything. Okay, so this message, when we just drop back out to command prompt, what it's telling us is that there's some additional packages that we have to run in order to be able to install the live camera scripts in order to make those run, the binaries for that. So we need to run this command. It's going to be this .miscellaneous build Indi-sh. And there's a way that we will do this to where it doesn't take quite as long as if you were installing every single bit of the drivers. But the command that I wanted to show you to verify that your Raspberry Pi cam is actually connected, you want to just make sure that the cable is connected correctly and all that. So if you type in RPI cam -hello, and we can say -- list cameras. this will show you your camera either is connected or is not. So if we type this command, and it shows us that it does detect the IMX477, which is the PiCam HQ. So we're good to go on that. But now let's go back to the command that we need to run in order to be able to continue our setup. So it's this command here. We're going to select that, and we'll right click. When you right click it, it copies it to your clipboard. So now we get down here, we can right click again, it pastes it for us. So we'll hit enter. And it's basically kind of showing some of the same information we saw with the setup, but it's showing you the details that it's going to have. It's going to ask for each one of these prompts. So we'll say OK. And again, you get a 10-second timeout period to break out. Okay, now this part, if we choose automatic, it will install the third-party drivers and all that. We really don't need that, not with the PiCam HQ. Now, if you're running one of the cameras that is a true AstroCam, like the ZWO, the Player One, any of those models that are true Astro cameras that connect via USB, then you will want just to go ahead and choose the automatic. But that does take considerable time because it compiles a whole bunch of other drivers that we do not need with our PiCam HQ. So I'm going to choose manual on this one. And we're only doing that only because we're running the PiCam HQ on this build. So we've got manual selected. We'll say OK. And then we've already checked the latest versions. We're going to say no on this one, just to speed things up a little bit. So it's going to go ahead and pull in some supporting files that it's going to need to have in order to complete these other setup processes. So this, depending on the speed of your internet connection, will determine how long this is going to take. Okay, so on this menu option that we have, this is where we can select the faster option for our particular setup with the PiCam HQ. We're going to choose the only Indi core. So we choose that, hit spacebar to select it, and then we'll tab down to OK. And this just only installs the Indi core. It bypasses the third-party drivers and things that would need to be compiled, which would add considerable time if you don't need it. Okay, and we will choose what the recommended version is. Okay, so it's finished all of the Indi core build install. So now we will jump back into the setup. So our command is /setup.sh. We'll hit enter. Again, we'll get the little banner telling us what the settings are going to be. Okay, we'll select our live cam. Spacebar to select it. Tab OK. Select the IMX477. Okay, we'll say no to this just for speed. And the setup process will continue from here. Okay, now we're being prompted to install any additional Python modules. And let's go ahead and say yes to this because you might not need them right away, but they are nice to have later once you realize what they offer to you. So we'll say yes to this. And then you definitely want the GPIO Python modules. Again, if you're new to this, you might not use them right away, but when you see what other people are doing with them, you'll think, yeah, I really want that. So we're going to say yes to that. Okay, on the GPS driver, we're going to skip that one for now. We do not have an actual GPS device connected to our setup, so we'll skip that. And this next prompt is, do you want to require authentication for just to view the Indi-Allsky website? If this is on your home local network, any family member can connect to your Indi-Allsky setup and only view the latest images and some of the videos and time lapses, things like that. If you say yes, then anybody that tries to access your site in your household will be prompted for a username and a password, which would be highly inconvenient. Now, you will still be prompted for a username and a password if you try to modify the system. But for this, we're just going to say no. And then do you want to configure OIDC? We're going to say no to that. Okay, now this is important. I'm pretty sure this will help determine when your sunrise, sunset, so that the system knows based on your location at what times to maybe switch between day mode and night mode. So you need to try to be as accurate as possible on this. You can go to any like latlongitude, I think .com or something like that. Just Google lat long, and there's plenty of sites that will come up where you can put in your location information, and it will tell you what your latitude and longitude is. Now, I would not recommend putting in your exact home on this. Just try to find maybe a nearby landmark or a large city near you. As long as you're within the vicinity, the the numbers will be accurate enough. But I'm just going to leave these as default because this is just a test system that we're building now. So I'll hit enter and then enter again. And then our geographic areas are the Americas. And time zone is correct, Chicago for me. Okay, now this is where we're going to specify our username that we're going to log into the Indi-Allsky web service or web server. So I'm going to just use Allsky again. Same thing as my Raspberry Pi login. We'll just type in Allsky, enter, and then the password, we'll use that really strong password as password. And type it again to confirm it. You can put in your full name here. We'll say Allsky. Say OK. You can use your personal email address. I'll just type in mine, but I'll mask it. And we'll say yes. Let's go ahead and restart the Indi server. And then we're going to say no to the MQTT broker. It's a pretty good data exchange service, but we're going to leave it disabled for now. And then do we want it to start automatically when it boots? Absolutely yes. And we would like to start it now. Yes. And then this is one where you remember the LEDs that I was pointing out earlier when you could see the activity, like the SD card being read. This gives you the option to either turn those on or turn those off. On my Allsky enclosure, the lights are kind of obscured down lower in the system, so they will not reflect any light up into the dome. So I'm going to say to do not disable these because I find these useful for troubleshooting things. So we'll just say no to this for now. And we like the system D watchdog daemon. Yes, we do. In case it gets hung up, it will automatically reboot itself. And yes, we do want to apply the optimizations. Yes, we do want to disable the GUI. The GUI does use some resources. For the most part, you're never really going to be inside of it. So we'll disable it. You can always turn it back on later. Just Google how to turn it on if you decide you do need it. So we will disable it now. Okay, so that process is completed. Now the next thing we need to do is just fire up our web browser and we'll go to the Allsky server. And this is basically the address. What it's telling you right here, that it recognizes your host name. And then this is the path inside the web server directory that we'll go to. Okay, now that we have our Indi-Allsky installed, let's go ahead and open up a web browser, and we're going to go to our host name that we've set up for the Raspberry Pi. So we'll type in https:// and my host name is Allsky. So I'll type that in, hit enter, and then you'll get a message about your connection not being private. That's because the server uses a local certificate, which is not really tied to the name. So that's fine. We'll say advanced and then proceed to Allsky. All right, so looks like we've got a good picture on here. This is at my workbench. You can kind of see some different options. You'll see the overlays, different things you have available, the moon status, smoke, anything like that, time and date. Now, because you're not required to actually log into this, remember we set that setting to where family members can log into your Allsky, but they can't make changes. So they do have options to look at the basic images, time lapses, things like that. So if we choose latest, that'll show the most recent picture. Loop, you can set this for how far you want to see back, and it will do a mini time lapse. You can look at your gallery. This will show your images that were captured through the night. And here you go. Here's a bunch of images that captured just looking at my ceiling. And just kind of other information that you can just click around and kind of see what's available in here. So now if you need to make changes, this is where the login is required. So down here at the bottom, we have a login option. So we'll choose login, and we'll type in our username and password that we set up during the Indi-Allsky setup. This could be different than your Raspberry Pi login if you use different credentials. So we've used the same username and password across all the installs. So we're going to say Allsky and password. Okay, and now you have some new options on here. You have system. Now, system is where you'll make configuration changes such as gain, how long you want your exposures to be. So we'll click on that. And you have max exposure set to 15 seconds on here. And then you could have minimum, maximums. And I'm not going to go through every single tab on here because it would add an hour to the video. But the developer's website, you can go there and just see all the different parameters. He has very good documentation that explains pretty much every one of these tabs. There's also a very active Facebook group. It's called Allsky. You can go in there and ask questions there. You'll normally get some pretty good responses from most of the users. Everybody's pretty up to date and up to speed as far as all the settings that you would need to adjust, especially if you're new to this. So we'll look at this next one, the image tab. Do you want to turn on or off daytime captures? A lot of these are just toggles to enable features, disable features, or change certain values. So that, as I said, I'm not going to go through every one of these. It would just take too long. So the main thing we're looking to verify was just, is our camera capturing? And yes, it is. So we were good to go on this. If you see your camera on the screen, you've successfully completed your Indi-Allsky server setup. I really wish 3D printers were this quick. Both of these components took about a day apiece. Now we're ready to attach the dome to the dome cap. And this dome I'll have in the parts list. It is actually sized specifically for this cap. So whenever you're using the configurator, whenever you size this, the default settings basically allow this dome cap to sit right inside this circle. Now you can resize the dome cap if you have a different size dome, and say your dome is a little bit narrower, say it's not this full radius that we have on this one. So if you need to resize it, you can actually bring these sides in the configurator tool. So this way you'll be able to accommodate maybe a smaller dome. It's going to be difficult to accommodate a larger dome simply for the size of this dome cap is a fixed width. It's not going to really work well to try to increase the size and still be able to mount it onto the body of whichever tube you're using. So the part number will be listed in the description. I'll have all the items that we're using on this build in the description with links to Amazon where you can pick them up. Also important is the sealant that you want to use. I'm going to use Lexel on this one because I've used it quite a bit in the past for other projects, and it does a very good job sealing plastics to other objects, whether it's plastic to plastic, plastic to metal. It does an incredible job of sealing things. I would avoid using standard silicone window caulks, things like that, simply for the fact that they can flex or crack at the most inopportune time, especially if it's raining. You don't want to have a leak in your seal. So Lexel has been a very good product for me to use. So what we're going to do first, this Lexel is very sticky and messy, so definitely put your cap onto some type of a table cover. You don't want to get this on your kitchen table or your workbench. And what we're going to do is we're just going to apply a thin bead around the edge of this. So we're just going to apply just a thin bead around this, and then we'll take our dome cap and seat it on there. And once it's seated, try not to move it. Let it start curing. Just set it off to the side and just let it cure for several hours. I would even recommend putting it on the body of the enclosure yet. Just give it a day before you do any kind of touching on it. So we'll go ahead and start this sealant applying. And make sure you cover all the way around. Don't let any gaps appear, because that could result in a leak in your dome, which is the last thing you want with your electronics inside. And I'm not applying this as cleanly as I could, but it's going to be up in the air and nobody's going to see how ugly it looks. The main job is the functionality of the seal. So we can see all the way around. We got the sealing applied. Look for any gaps that you may have in there. You don't want to have any gaps at all. And the sealing this side here could actually use a little bit more. Like that on that corner. And on the dome cap, it comes completely wrapped in plastic on both sides, this side here and all the way around the top. It also has a kind of a plastic wrap that only covers the top. I pull all the plastic off with the exception of the dome cap plastic. I leave that on just so that I don't accidentally scratch it while I've got it on my workbench or any areas that I'm maybe working in. So once you're ready to apply it, push it on there and push it down with good force. You'll probably have some squeeze up on the edges, which is fine because our lens is not going to be looking at that side of it. It's going to be above the rim of the cap. So push it on, make sure it's good and secured in there. And it feels like you can feel it moving inside the ring itself, which is fine. The outer ring where the lip of the dome is. Actually just about 1 millimeter on each side gap. So that should be good. You could wipe this with your finger, just wipe the edges to catch all that. If you just wanted to make it look nice, make sure you have a wet rag nearby that you can wipe your finger off with, because this stuff does get nasty. And as an example of why you want to keep that plastic on there, if your fingers have any of this Lexel on them, you don't want to touch the lens, because if it dries up here on the dome cap, you will definitely see it in your camera, and it is very, very difficult to get off cleanly without scratching the dome. So yet another reason to keep this dome plastic on top while you're applying it. So that looks pretty good. I'm gonna just push this off to the side, let it cure. I'm probably just gonna let it cure for a full day just to make sure that there's no issues with me bumping it and trying to put it onto the housing early. We still have a lot of work ahead of us, so it'll be fine to cure off to the side. Okay, we're to the part where we're actually going to build our Allsky. These are all the components that you would need. Not everything is required. Some things are optional, and I will point out which things are completely optional. It just makes life more convenient after you get one of these set up. And if it's far from you or if it's high in the air, you don't want to have to climb on a ladder to reset things. Some of these components will make life easier. So let's get started. The very first component we have here, this is just plastic glue. This will be used to glue the screen to the enclosure. So like on the bottom of this enclosure, this is our fan hole. So the fan sits on the inside. We need to have a screen on here so that we don't pull bugs and other things into it. To make the screen cutting easier, I have these templates here. This basically is the width that you would need for the actual tube enclosure part. You would actually just cut 2 of these. So you'd print this out. You only need 1 to actually print out, but basically put it on the screen, cut it, and then put it again at the end of that, cut it one more time, and that's the exact length for the circumference of the inside of the tube. This bottom part, this is basically put this down on your screen, cut around it, and that screen will fit perfectly inside of here. You can just put little dabs of glue kind of on some of the support parts, and when you press the screen to that, it'll seal tightly. And there's also a stencil for if you're printing the standard tube, the vents on it has the same vent ports on the neck of it that the tall enclosure have, but on the bottom, the ports are actually around the edges like this. And on that system, it's really designed for kind of a chimney effect where it's a passive heat transfer. So as it warms up inside, air will pull through it and move itself up to the top. Hopefully that makes sense. Let's see, other components, the wire that we'll use, since all the internal wiring, it's a very short run, so 16 gauge is more than adequate. You could actually go with an 18 gauge if you wanted a thinner wire to work with. This is our power cord that we're going to use. Now, at my observatory, it's an off-grid observatory, so everything runs off 12 volts. So all the components that you see here are also 12 volts. So a 12 volt system just natively supports this. If you're running off of your house power, you've probably got a 110 connection. You will need some type of a 110 to 12 volt converter so that you can power your equipment. Obviously, you don't want to throw a 110 plug into your power distribution block and try to power this other stuff. You'll see a lot of smoke and sparks and probably a fire. So with this is basically just the cable that will run up into the housing underneath. And this is just a quick connect. It's a weatherproof quick connect. So on this side, you have the positive, and that's the positive lead going up in there. On the other side, the positive lead coming from the battery would obviously be protected. So it'd have this rubber part on this side, and the ground would be exposed like that. So the two would be able to mate together here. Let's see what else we have. Our O-rings. So this is on the bottom O-ring for the tall enclosure. This would basically just kind of sit down here and rest on this little ridge. And all this does really is just ensures a good seal so that if you have bugs or something that go past the threads, they shouldn't be able to make it past this thread on here. Now, this top one, this black one that we have here, this one actually goes on the top of this enclosure. So when you put your dome on, you screw it down, it'll seat tightly to that. So now both these rings, the top O-ring, the cap seal that we'll call it, it is a 112 millimeter inner diameter. So it just sits on this ridge, and when you put the cap down, it seals tightly on that. The thickness of this cord is a 3.1 millimeter, but I will have parts linked to these that you can buy these directly on Amazon. But if you have a TPU filament on your 3D printer, you can certainly print these yourself, and these templates are included in the SkyForge designer. So just pick those from the list, send it to your printer, and it will print. You can print these if you have the TPU filament for that. Otherwise, you can buy these directly off Amazon. I think you have to buy probably like a 5-pack of them or something like that. See, next we have, now this is completely optional. This is a thermostat that actually controls the fan, turns the fan on and off. Now, you can control fans with your Raspberry Pi based on temperature, but I do not run this camera during the daytime. This camera is only a nighttime camera, and since it's a astrocam, it doesn't really make pretty pictures during the day. It's really geared towards the night sky. So with this, during the daytime, even though everything is off, I still like to keep the enclosure cool. So if it gets above 100 degrees, this little thermostat kicks on and it turns our fan on. This little fan that we have here, it will turn it on. After it reaches, it will get up to whatever temperature. Say we have the threshold set at 100 degrees or 110, it'll turn on until it gets all the way back down to 95 degrees, and then it shuts off. And it just repeats that process all day long. Now, there may be certain days where it's extremely hot outside, and once it turns on, it doesn't turn off until nighttime, but that's fine. We're keeping airflow running through there and kind of keeping everything overall kind of cooler in the box. I won't say cool, but cooler. And see, that is an optional item. You do not need that. You could certainly, if you're running your Pi during the daytime, you can certainly have that turn on the fan for you, but I don't run my Pi during the day, so that's why I have that device in there to help control the fan. This is a buck converter. So this is basically what you're looking for on your Pi power supply. You want to make sure that it can put out at least 25 watts and it has a 5 amp output. This is crucial because if you buy a cheaper model, they may only have a 2 or a 3 amp output, and it will probably only output 15 watts. Your Pi, if you're using a Pi 5, you'll likely reboot throughout the day and night because it's not being supplied enough voltage. So you need to make sure that you get it's the USB power. It's taking 12 volt, converting it down to 5 volt, giving the Pi sufficient power to actually run. Next, we have screen. This is the screen material that we'll put at the bottom of the cradle and then at the neck of the tube. Wire strippers. It doesn't have to be this style. It could be any kind of decent wire strippers. And then I think we already covered the electrical wiring. This is an M12 bolt, and it's a 1.5 millimeter pitch. And the reason you want one of these is if you do 3D print this yourself, this hole right here, I've printed threads inside here, and it's 12 millimeter threads with a 1.5 millimeter pitch. Some printers aren't very accurate when they're doing this, or they can kind of get some debris inside there. So when you try to put your wire gland in there that you're going to run your power through that, it may not thread very well because you're going to be trying to twist plastic into harder plastic. So if you have a steel bolt, you can just thread that in there. It just cleans up the threads. That's all we're doing with this bolt, is just making sure those threads are good all the way through. And this way, when you put your wire gland in for your power supply wire, it'll be nice and clean, and that will thread right in. So that's all this bolt is for. And it's a 12 millimeter with a 1.5 millimeter pitch. So this is the wire gland I'm talking about. So we'll take this nut off the end of it, and you'll see it's threaded. Let's see those threads. And what that does, that basically just threads right into this hole. It's hard to do with the camera right in my face, but anyway, yeah, it'll thread right into the hole. Just make sure you don't cross the threads. And basically, your power wire will run through this little hole, and as you tighten it down, it just secures it tight so that dust and spiders and stuff like that can't get into your enclosure. And normally when you buy these, you probably get 20 of them for $5, but you'll have further projects in the future. This is going to be our power distribution block. So what this does is your positive and negative, you decide A or B. I always just do the positive on the A side and negative on the B side. So where your power is coming in through the bottom of your enclosure, the red will go on that side and the black will go on the B side. And then when you look on the sides, you have these little labels. You have A4, B4. So A4 will be a positive, B4 would be a negative. So each device that needs positive and negative coming out of it, you would just insert them to those little sockets, tighten down the screws on top to secure them in, and you're good to go. That's a required part. Now these are extremely handy. I use these all over my farm. These are Wi-Fi power modules. So what these do is they'll just draw power from your power distribution block. This is a single module one. You'll see this is a dual module. They have a 4 module, and I think maybe an 8 module. I can't remember if I've seen up to 8, but I know I have single, duals, and quads. So these are really nice because when you power them up, you can connect to them on your phone and program them, and you can set schedules for them. You can remotely, if your Pi is hung up and you want to reboot it, you don't have to walk all the way to it or climb on a ladder to get to it. just hit the power button and it shuts it off. So anything that you have on here, like with this dual module, you would have inside the app, it would show this module and say switch A or switch 1, switch 2. So you could actually have your devices powered through these ports, and I'll show you how to wire them. It's pretty straightforward. But you could say turn switch 1 off, but leave switch 2 on. So you could have like your camera on one. If you have like on my 533, it's powered separately from USB, so it actually has a power connection on it. So I could have, say, my Pi running on this one and my camera running on this one. If the Pi is messing up or if the camera's messing up, I could just turn whichever one I wanted off. Could turn the schedule on both to be off, and that's what I do now, is that I have my Pi set to turn off in the morning, say around 9 a.m. It has a cron job that shuts itself down, and then 9:15, it automatically kills the power to it through a scheduled process that's built into the device. So these once you connect them, you don't have to mess with them on your phone anymore. You set schedules and it runs automatically for you. And they do run on Wi-Fi, so you don't have to have any kind of special radio or anything to communicate with them. But yeah, they're very nice modules to have, even if you're not using them for a project like this. If you have something that you need to remotely control, power on, and set schedules, you can do it with that. And those are both optional, but I'd highly recommend they're not very expensive at all. This is a PWM controller. This is what we control our output of our dew heater with. So you can see it when you'll hear it maybe click, that when you turn it, say about halfway up, that's going to send half of your 12-volt power to your dew ring. Whether you did a DIY dew ring or you bought one from the dew control people, it's good to have one of these because you don't usually ever need your 100% power to your dew ring. Normally about 50% is sufficient. You're just trying to heat the dome up just above the temperature on the outside to keep dew from forming. So it's a very nice module to have, and especially with my 12-volt system at my observatory, we need to control as much power usage as possible. So if we don't have to have something at 100%, let's not have it at 100%. And obviously this is the brains behind the system, whether you're using it in an enclosure or if you have a mini PC. This is what I'm using. This is a Raspberry Pi 5. And this is the NVMe hat that's on it. Just gives it a little bit more robust storage, a little bit more storage. And I feel comfortable with trying to run on an SD card, especially for if you're doing a lot of intensive writing with it. But very nice little setup here. And let's see, of course we would need various tools. We have Phillips head and a little flat head, different lengths depending on which components you're going to try to get to. Various screws. Most DIY people always have a drawer full of screws, so the chances are you probably have the screws and things that you would need. I'm very clumsy, so I keep these screws in bags. I don't know how many times I've spilled this tray and they've gone everywhere. Let's see, what else is there? I think that is it. So we will go ahead and move to our assembly part of this now. We will kind of template out how we're going to mount to these various components. One thing that you'll see on here is inside here, you can see there's some little holes down there at the bottom, little pilot holes. That's where the fan will sit at. And this is for a 60-millimeter fan. So this fan will go right down here into the bottom. And the pilot holes will line up directly underneath that. And this is a low-profile fan too. So in this build, my 533 is a very tall camera, so I can't have it much taller than this because the tube wouldn't slide up into the tube. You'll see that where the Raspberry Pi actually mounts at, back here in the back, we have these little holes here. Those are pilot holes for the Raspberry Pi to connect to. So if I had a much higher fan, this is a low profile here. Some other fans that I have are like twice this thickness. If it got any higher, I wouldn't be able to put the USB cables into the bottom of the Pi. If you're just running an ASI 676 or one of the PUC type cameras, you're not gonna have that problem at all. You've got plenty of room to work with, but this is the max height that I could have on this particular cradle with this particular camera. And of course, this is where your components could be mounted to. You have all this space. You could mount from the inside as long as you're not crossing over and punching through the board into another device on this side. That's, of course, you have that side, and you have a small panel here that you can work off of too. Everything up here, this is where the actual camera sits at. So these little fingers that are right here, these little 3 sections, those are what actually hold the camera, and they hold that camera very snug. And it'll be the same way with your ASI, your Player One. Either the round ones or the hexagon ones will fit snugly into their respective holders. So that is that. Next, we will start working on laying out how we are going to mount these individual devices in there. Okay, so the first thing that we're going to install into our cradle is going to be this fan. This is our cooling fan that we will have hooked up to that little thermostat that I was talking about earlier. Now, this fan, I do not know which way the air blows. So that's an important factor on determining which direction this sits inside the cradle. I'm sure somebody probably knows the standard, like if it labels on this side, fan air blows this way, or maybe it's the opposite. I just don't know. So we're going to test it before we actually install it. Now, where this fan actually goes is down here in the very bottom. You'll see these little standoffs down there. Those are little bosses, little screw bosses that this fan, I've configured this cradle to sit on. Now, this is a 60 millimeter fan, and they generally have the screw holes in the same. They've standardized on that, fortunately, for most of the vendors that I was looking at. But basically, it's just going to sit down there in the bottom, however it goes, this way or the other way. Just sits down there in the bottom, and it will draw. My plan is to pull air from the top down. So when the tube is on here, when this is sitting up in the tube has those holes around the neck. It's going to draw air through that, down across all the components to keep everything cool, and exhaust it out the bottom. The reason I want it to exhaust out the bottom is I don't want air or dust or anything like that to be taken from here and blown up into the dome area, because it probably look like those confetti balls the kids used to roll around where things are just popping up in the air. Don't want anything like that. So I'm just going to take the air from the sides and pull it down across the components to keep everything cool and exhaust out the bottom. But first, let's figure out which way this fan actually blows so we don't install it into the cradle upside down and then have to disassemble it, because once it's in the bottom, it's going to be difficult to reach around everything. Okay, so what I have is, I think I talked about these a little bit ago. This is the standard quick connect that I've standardized on my farm out here. And then I have these little battery cable type things that will just connect directly to the leads. So we'll connect these two together and make sure this is off. We don't want to have an arc or anything. The power button's off. So we will just connect these two together. So you see how the red on this one is insulated coming from the power side, and then negative, and this is the red on this side. So these will just connect together. Quick connect creates a weather tight seal, and then we will hook up our fan. So we have our black cables here, our black connector, black wire goes to that side. Make sure it's snug in there. And then we'll go to our positive. Make sure that one's snug. Okay, keep those from touching each other. We don't want any fireworks. So we'll hit our power button and look at our fan. I will say one of the good things about working with 12 volt is it's very difficult to hurt yourself. Don't get me wrong, it can be done. I'm sure there's a lot of stories of people that have done it, but if you're careful, it's not like you're dealing with 110 or 220 or anything like that. It's very low voltage and you're usually not going to get hurt. So we'll hit this. Okay, fan's on. Yeah, it's definitely, air is blowing this way. So this side of the fan pushes the air up. So we're actually going to mount this facing down. Man, that blows out a lot of air. That's really nice. I wasn't sure how good this little low profile fan was going to be, but yeah, it blows air very nicely to the bottom. So that will definitely help keep things cool. All right, so we're good to go on that. This just kind of sits right down here in the bottom. And there's these little screw bosses that it should line up. Yeah, it lines up perfectly on that. I don't know if you can. Yeah, those line up perfectly. So we'll go ahead and screw those in, get that bundled up. And I'm probably not going to show this process. You can kind of figure out how to get your screw or how to get your fan screwed in and all that. But some of the stuff I'm just not going to be able to do with the camera running because I need to be able to see over it. Okay, so the fan is secured in there. It's holes lined up perfectly. Now, the next thing we want to install, since we have that in there, we want to install our Pi. The Pi is going to be mounted facing downward like this. It's the holes that I have in here. And let's see if you can see these 2 holes, 4 holes actually. There's a pattern for all 4 screws of the holes on the Raspberry Pi. Now, on this one, I do have an NVMe hat on it. Some of the holes are being occupied by screws that hold the hat on with the standoffs. So what I'm going to do, I'm going to not use the standoff on this corner. This hole on this side is already free. So I'm just going to use 2 screws to hold the Pi in place. And that's more than enough. This thing's not going to be bouncing around or anything like that to where it would ever come loose. And what I'm also going to have to do, because the hat is directly over this hole here that I need to screw into the support on the back of this cradle, I'm going to just loosen it so it drops down just a little bit out of the way so I can get a screwdriver into there. And of course that one will be no problem. But that's going to be our next process. So we will basically mount that into the very back here, and then we'll come back to that, and it'll be completely mounted up. But again, some of these steps does not require me to do it while you're actually watching. You can obviously see how it's going to be supported. So, all right, we'll come back to that one in a second. Okay, so I've got Raspberry Pi installed. We tacked it on the pilot holes that we already had drilled on there. And those are M2.5 screws. They're about 10 millimeters long, and they're the M2.5 diameter on there. But one thing I will point out, this is an early prototype cradle, and whenever I was designing this little gap, I thought this was large enough for the power supply plug to actually go in. I didn't bother measuring it, which was a mistake on my part. So there's a little jacket around the USB-C connector there, and it's wider than what this gap was. So I had to actually cut out some material here just so I could get the power to plug in there. Now on the new STL files, this is already cut out. This is already pre-cut out, so you don't have to do the little engineering that I did here. Basically, it'll start down here at this lowest HDMI port, down this port 2. So here's port 2, here's HDMI port 1, and there's the actual USB connection. My lighting is terrible right now, but there you go. You can see it there. Power, HDMI 1, HDMI 2. This whole section is cut out on the new STL, so you will not have to do what I did here. Okay, so next what we're going to focus on is getting our power block installed. So I've already pulled the power wire in. It's got a little 12 millimeter cable gland. Remember, it threads up into this port. It's already pre-threaded. That's where you'll use your 12 millimeter bolt to clean the threads and make sure everything's good. And we'll have these just extending up into here. And what we'll do is we'll connect those to the bottom here where it says port A and B. So on our system, A is going to be positive, B is going to be negative. So I'll move the red cable, the red wire to the A side. The the black wire will attach to the B side. Now, if you've never used one of these before, it's a pretty simple concept. Let me get this over into the light so we can actually see. Basically, when you thread these in and out, there is a little screw or a little cap that tightens in there. So as I thread these up, see how that tightens it up? See how that closes that gap on the B side? If your wire was in there, it would be getting squeezed and held tightly in that little bitty hole. Do that again just to make sure that the camera can actually see it. We'll tighten that up. That's tightening it clockwise, and then counterclockwise will open up the hole so you can put your wire into it and clamp it down. So that's pretty much how, and that's the same concept of these ports on the side. So you have your A4, B4, A5, same way it's all labeled on each side. And you'll basically just tighten these screws on top to actually clamp the wire down. So turn clockwise to actually tighten it and clamp the cables in, and then turn counterclockwise if you need to release the wires. So, all right, so this is going to go, basically it's going to install right here at the bottom, and so your power comes up to the bottom, goes immediately into this port, and then from there you fan out your power to any device that needs it. So we'll go ahead and get this installed, and we'll be back to that in just a second. Okay, so I got this power distribution block mounted. I was going to mount it down low, but when I actually put it down there and I did a dry fit of putting this cradle into the tube, there's a ridge on the bottom of this tube where the O-ring sits at, and that was just too close to where these things protrude out. So when it was down here, it was actually interfering with that O-ring ridge. So I've decided to move it up, and this way it's got plenty of clearance up here in this area where the tube is much wider, so you see it easily passes that. But once those two kind of start trying to connect together when you're threading it in, this O-ring ridge was actually hitting those tips. So I decided just to move it up. It doesn't hurt the overall design of anything. It's just making things fit when you have very little space overall to work with. You want to optimize anywhere you can. So with that was basically just one revision in between the last video that we just started. So now we're going to start installing these power Wi-Fi modules. So I'm thinking this small one would go very well right here. There's actually two holes. You can see there's two holes right here. So those that's the only contact or connections they have. So I'll probably put a double-sided tape pad on there just to kind of hold it in place, and then we'll get those screws threaded in there, because the main parts you need to access are this back side. That's where one device would power into, and then of course this device, this is where it gets its main power from to control the relay, the Wi-Fi, and all the other components that are on the board. So our next process will be attaching that. Okay, we've got the Wi-Fi power contact secured onto the side of the supporting boards here. Now, one thing I do want to point out on here, as you install these components, kind of look down the ridge, tilt it down, and just make sure that you don't have anything sticking out that could actually obstruct the tube from coming down on this. And even better, just do a dry fit. So I'm going to take this, slide this up into our tube, and make sure this thing still threads in. Yep, we're still good there. Nothing's blocking it, and it slides right in, because nothing worse than getting everything assembled only to find out that you've got one or two parts that are sticking out into the channel that could actually block or obstruct the tube from being able to slide over it. And then one other thing I want to point out is I failed to do this. This cable gland, once you get the power in there, you do want to make sure that you secure this cable gland. See these little fingers on here? As you put this nut on here and you twist that down, it's kind of tapered inside here, and it will start squeezing these fingers down really tight to where this wire, it would have a very, very difficult time pulling it out, because you don't want to actually snag this wire to have this get yanked out of your power block. And you don't want to have any kind of a situation where these things could get loose because this cable is continuously being yanked when it's not secured. So just push that up on there and tighten it up. And as you tighten, it will tighten those fingers down, and you'll see you have already a little slack left in here just in case, a little stress relief on the cables. But once you tighten this up, you'll be very hard pressed. You will definitely have to really be trying to get this to actually pull out and potentially separate from up in here. And I do have a little gap on that cable. I need to get that pushed up in there just a little bit tighter, but you definitely want to make sure this cable gland is tightened so there's absolutely no way this cable can accidentally get tugged and yanked out. So we'll go ahead, and next step, we're going to wire this in. We're basically just going to connect our positive and negative ports on here. And let's see, I'll probably look at the documentation. I don't see a positive or negative. Normally positive, it will be on the side, on the left-hand side. Let's see if we see that there. No, nothing's written on there, but I'll look at the documentation, but pretty sure this is going to be positive and that's going to be negative. On these two right here, positive and negative. But I'll confirm that with the documentation. Okay, so the first wireless power module is connected. So this, I could definitely have made this wire shorter, but I started kind of getting into a constraint of being able to split these wires far enough to where they didn't become two independent wires, because just trying to split them, trying to get the wire cutters on there, wire strippers on there, it was getting a little bit further down. So that's fine. It's not protruding out into the actual area where the tube, where the slides up in the tube is going to get at. And if it does get in there, you can always just kind of use a zip tie to kind of just push it up like that to where it's not sticking out past that pillar. But this is fine. It's fine to sit just like that. We don't want to have it too much stress on that angle, because it could end up over time causing wires to where they may want to pop out of their socket and shut off power to that. So, all right, so now I guess we can look at the other side. We have several options. We still have, let's see, we have our Raspberry Pi power module that we need to connect, and that is a USB cable. And of course these wires, they need to be able to somehow get over there to, they're actually not going to go to that side. The Raspberry Pi power module is actually going to connect to this module, which is going to be on the same side as it. That's, what we're going to have is the Raspberry Pi will connect to one power module and one power switch, and then the camera will actually connect to the second one. So what we'll do is we'll mount probably this something kind of at an angle, because it's a little bit wider than what the plate is. So we'll do that at an angle, and probably try to catch this one somewhere down here like that. And we still have, let's see, we still have a PWM module that we need to find a home for. And then we also have this thermostat module that we need to find a home for. But I actually think I've got a pretty good idea where this can go. This can actually sit kind of like this. That was one of the things when I was designing this. I wanted to have a little tray where that could sit easily and not kind of have to figure out at the last minute where that could go. But that drops right into that little tray there. Of course, if you don't choose not to use this module, and if you're using a dew sensor or something like that, you could, of course, strap that there instead. But you also, just keep in mind, you also have the whole inside of the board. Just be careful when you're putting your screws through there. You'll probably want to use some glue or standoffs or something like that, because the screw right through that would get into your power module and, of course, into that little guy there. And of course, not everybody is going to be using a 533 camera. So this camera really constrains you as far as the amount of space that you have in here. You could go much taller with a standard cradle, or with the tall cradles. You have much more room. This is everywhere where the camera is sitting at. This could actually go way up and give you a lot more space for one module. So with the 533 build, you are constrained for space, unless you have a bigger printer. My printer only prints up to 254 millimeters. So if you've got a printer that prints very tall, sky's the limit as far as your tube size, right? Okay, so we'll go ahead and work on getting this one mounted in here. And this is our Raspberry Pi power. And then we'll do our dual channel Wi-Fi power module. Will probably sit in this area. So I'll go ahead and get those two bolted in, and then we'll come back. Okay, so both these modules are mounted now. So this is our wireless power relays. So whenever we can set schedules and things, these things will automatically turn on certain devices. We can reboot the device if it's not responding, camera's having issues, just click a button, power off, power back on, beats walking out to wherever you've got your All-Sky enclosure set up at, and climbing a ladder or whatever. I know in my situation it's about a quarter mile away, so definitely don't want to have to make that trip if I don't have to. Now, we'll probably be doing some zip ties and stuff to kind of manage the wires. It's always a mess trying to make everything look pretty, but you'll do your best whenever it comes to that time, trying to get the wires tied in, make them nice and tidy, because you definitely don't want them hanging out into this area where the enclosure will be coming over. So we'll make sure those are nice and tied up against that. So we'll go ahead and string our power cable wire across. We'll probably go up, over, and then back down to one of these. And I will mention, I forgot completely to mention this a while ago, whenever you're tapping your holes, use a drill. Don't try to force the screws. Don't just start trying to make your own holes with a self-tapping, because this filament it's plastic, and it can be like wood, and it can split. So if you're too close to the edge and you try to force a screw in, there's a good chance you may crack that out. So go ahead and use a drill to drill your hole, and then use your M2 thread or whatever type of screw that you're using for your components. I'm primarily using the M2 class. I've got M2, M2.2, and M2.6, depending on the size of the holes. Some of these holes are only M2s, and then some of them are all the way up to M3s. But I've just got a washer on these holding this in, but these are just M2 screws. And you see they do poke through just a little bit. Nothing's on the inside that would be affected by that right now, so that's good. And so far I'm happy with the way this is looking. Kind of had an idea in my mind how this was going to look, and it's coming around. It's working out well. Of course, everybody's going to have their own style of how they want to do things if you choose to use this enclosure. But again, this is not the best case scenario with this particular enclosure, simply for the fact that it's trying to support a very tall astro camera. You would actually have way more room than what I'm showing here if you chose the default size. And of course, you can make these things smaller. I'm actually printing one now for my HQ Cam, a friend of mine's camera setup. So his is actually going to be much shorter. It's going to be a very compact design, but still using the kind of the wide body version where this slides up underneath there. He does want everything to be self-contained in his unit. He doesn't want to run a separate system outside of it, so everything will be self-contained in his also. So I think it's looking pretty nice. Okay, we've got the power Wi-Fi module wired in, and you can see it's kind of just wraps across, zip tied up, over, around, and then goes into these other ports over here. The power cable is the same thing, USB cable wrapping around, taps in there. I really wish they had a right angle adapter for this. I don't really like putting that big of a kink on a USB cable, but I guess we'll see how that pans out. I don't think it's going to cause a huge issue, but over time, who knows, it may degrade the quality of the wire inside just being pinched like that, but we'll see. And then let's see, what else have we got? On the current STLs, if you decide to print one of these, you will have a much larger channel, so you probably wouldn't even have to go on the outside. You could come up through the middle and just come out and then back into that, because this channel here would be wide open for you to be able to work with the HDMI ports and the USB-C port on there. So yeah, we've got all that wired up. Everything looks okay there. And then I guess next we'll go ahead and wire in our thermostat, and then get our power and things connected on that. This is kind of a unique setup on here, and I'll go through how the power cable and all that connects on here. But we'll go ahead and get that fitted in there and wired up. And then after that, we only have the PWM controller to hook up. And then of course I did another dry fit, as you would expect with wrapping these wires around the outside. This is actually going to tuck into the inside of that pillar. But with this USB cable wrapping around like this, putting it in there, you kind of just tilt it a little bit to get past this lip that's right here at the right inside of here. There's kind of it's that O-ring where it seats. Just kind of tilt it up on one side, and then it'll slip in there. And then of course just make sure it. All right, well, we'll go ahead and work on the thermostat now, and it's going to go right here in this little plate here. Okay, we've got the thermostat sensor connected now. Now, if you look in here, let me turn this upside down. The writing's actually upside down. If we're looking inside here, you see we have a K0, K1, positive 12 volt, and a ground. So those correspond to each one of these connections on here. So now the fan that's coming off of this is this real skinny red wire. This is going down to the fan. It's going to go into this first terminal, this K0. The ground, obviously, is going to go to the ground side here, but it's also going to share that with our power connector that we're going to run over to our power distribution block. But the unique thing on this situation is these two in the middle are both power. They're both positive. So on that, we're going to use a Fort terminal, and basically we'll just slide right up into that. I can see it there. There we go. It'll kind of connect up in there, and we'll just tighten both those screws down so that they're both getting power to the device, but instead of running two separate wires, we're just going to run one with this one little Fort terminal. We will tie that in. We will run this negative over to this side, and we'll probably just twist in the ground on the fan with that, and then we'll run our fan positive over here. Once we actually get up and running, I'll show you how to program this device. There's also another little connector, and of course I forgot to connect it. It's this little white lead right inside there. I'll have to pull this out and reconnect that, but basically it's your thermostat sensor. It has to be able to have a sensor to tell it what the actual temperature is, but I'll pull that out and we'll get that reconnected. But in the meantime, we're going to go ahead and get these also connected to our power distribution block. So we'll come back to that. Okay, so the thermostat is wired in. Unfortunately, I did have to shift it over just a tad, because if you look down here where that thermostat cable needs to plug in at, I needed to be just a little bit more space right here. So it's still tacked in. It's got a screw holding it. It's not going anywhere. It's just not pretty, but at the end of the day, it's going to be hidden inside the tube, and I'll just tell everybody how pretty it is. But yeah, I think we're good to go now. So that is wired in. You can see that we've got that Fort connector that I was talking about, that Fort Spade, how it runs up over here and plugs into the positive, and then the negative wires running up here into the negative, and of course the fan is just sharing that negative port, and then also the positive port that turns on once the thermostat temperature reaches 100 degrees. It'll kick power to that lead, which will in turn the fan on and then cool the whole system. Remember we face the fan down, so air draws in through the neck of this tube, and then it flows down through some of these holes on the top here, and then kind of right down through the middle, all the way down the bottom. And it really moved a lot of air. I was pretty impressed with the size of that little fan. You can see it from the bottom. We still got to put some screen on there. We don't want bugs and stuff climbing up in there. I actually had a situation on my old Allsky system where I forgot to seal the cable gland all the way. I forgot to tighten it up, and there was this little spider that got in there, and it was one of the nights of the Milky Way, and of course it got up into the dome and spun a nice little web. And I was just like, the next morning I was like, oh, he's just a spider doing spider things. It was all good. All right, so we will go ahead and move on to connecting our power relays now, and I'll go ahead and get these two connected, and then we'll go over which ports these plug into, because there's 3 ports on here, but only 2 of them are actually used. And we'll actually pull power over to that, and it'll make sense once you actually see it. Okay, so now we are ready to wire up the wireless power relays. So this is a dual channel, and you'll notice up here at the top you have 3 screws and 3 screws. So each set of 3 screws corresponds to the relay that it's sitting under. And the way these wire up is, if you're looking at it from this position where the main power lead is down at the bottom, these are at the top. The first screw for both of these is basically where the power for the device that you want to send power to goes into. So for this, the USB relay that we have that will provide power to the Raspberry Pi, this red cable would go in its first connection. When we hook up the camera, its red lead would go into this port. So basically just pop that into that port or to that socket, tighten that down, and then that'll be the part 1 of connecting the power to this device. Now the second screw, we don't use the third screw at all. The second screw, we wire that directly into our power block. So we will take a wire, run it all the way over, and connect it into either A5 or A6, depending on where we hook this negative up at. So basically, the second port, you need to provide a constant power source to this block. So whenever this relay switches on or off, it takes the power from that block and basically kind of transfers it over to this little slot here. So it's got power coming out of it, provides power. Now, you'll notice we're not hooking up a negative anywhere on here, because the negative just goes straight back to the power block for the negative on the power block. So you'll recall our system, our schema, we're using A is the positive and B is the negative. So we just take this ground cable, the ground wire for this power block, plug it into the B6, and that's all we have to do on that. So we'll go ahead and get this wired up, and we'll be back to it in just a second. Okay, so that's wired up now. So this is our power block that will power the USB-C on the Raspberry Pi. You see this first lead coming off of it is going into the very first outlet, and the second lead, also a positive cable, is going over to our power block. Of course, the ground coming off of this is also going straight to the power block, because obviously it needs a ground and a positive. So this is connected to the block full time. This is going through the power relay. So when that switch kicks on, it takes power from this wire and then transfers it over to that. So this is how you could actually reboot this device remotely using the app. Now, I will point out one more thing. If you're manually activating things, you can hit these 2 buttons right here. So this little button here corresponds to that switch, and this one corresponds to this one. Now, what we want to do real quick, let's just do a sanity check just to make sure that we've got things wired up correctly, and we want to just kind of check for power. When we hook up our power to our Jackery unit that's down on the floor, these lights will light up as soon as I hit the switch. So I'm gonna go ahead and power this up, press that in, and I'm gonna reach down below and hit the power on switch for the Jackery for this. Okay, so you see the little lights flashing on here. That's telling us we got power on that. And this light will blink continuously because it's in a programming mode. Once it's actually programmed and it connects to Wi-Fi, then that light stops flashing. Same thing with the unit on this side. We got the flashing on that. And if you look right down into the bottom down here, you can see our thermostat. It's on right now, and it's upside down, but it says 29.4 degrees Celsius. That's the current room temperature based on what this thermometer up here is reading. Now, that will be programmed. We're using these little buttons right here, but we'll work on that in a little bit. So we're in good shape. Yeah, these lights will continue flashing until it actually gets a Wi-Fi connection and set up and configured. So that's good. And then if we look inside of our Raspberry Pi, actually it's not on, so we'll go ahead and boot up the Pi. So let's hit this button right here. You might hear a little click. Okay, so that, you see the little light came on. That's telling us that we have power going to this device. Now if we look on here, turn off the light for just a second. Okay, so you see the NVMe light flashing on here. So that's telling us we have power running to that. And of course, on the other end, right there, that's our Pi LED telling us that we've got a system that's booted. All in all, everything looks good. A little red light kind of shining through the translucent material. But yeah, everything's working so far. So we'll go ahead and turn the lighting back on and work on wiring our next wireless power switch. Okay, now we've got the dual Wi-Fi controller wired up here. So you can see on this one, remember first block we hooked up our Raspberry Pi power supply here. Now this one is our camera power. So this wire is just a barrel connector. It'll run right up through the top here because this is where the camera power port is. And it's the little skinny wires run to the very first port here, and then the main power wire runs back around over to your main power block. So that's pretty much the setup on that. Now the last component to hook up, and it will go right here on this A3B3 to get its power, is our PWM controller. So you'll recall this is the device that actually controls how much power we send to our do ring, because we don't want to have it wide open because we don't need that much power going to the do ring. The enclosure itself, all the components inside of it will generate its own heat. Just with the Pi running, any of the electronics running will generate heat. So some heat will already be there traveling up to the dome, but this will just add supplemental heat with our do ring. And if you look at the back of this, these type of applications have many different purposes. So if we look at the power on here, it says on this side closest to where the spinner is at, this is our DC in. So this is where our power into the device would be coming to. And then of course it has the positive and negative on there. If you can see that just on the right hand side, that's the positive, and on the left, that's the negative. And on the output, it shows motors, because you can use PWMs on motors to control speeds of them. It's just doing the same thing that we're doing with the ring. We're just limiting how much power we're sending to it. So we're going to go ahead and mount that inside. And I'm thinking probably we've got this little gap right here. And if you'll recall, this PWM controller only has a single hole right here by my thumb where it mounts to something. We're going to use a double-sided tape pad for this, plus that screw to keep it secured to the wall. But I'm thinking probably right here, mount it right there, because that will have there's a little void right here beside the Raspberry Pi power supply. We can screw through on this side through this and have it and make sure it doesn't hit anything on this side. So I think that's where we're going to go with that, and I'll get it all wired up and we'll anchor it in. And pretty much the only thing we have left is really to mount the camera and power everything up and make sure that the Pi sees the ASI 533 camera and everything else powers up. So we'll go ahead and do that. Okay, so I've got the last of the power Wi-Fi modules installed here. This one is actually controlling the dew heater. And the reason I did not use a 4 connector, we could have used a 4 connector on this one for additional components. I've had issues with the dew heater being connected to one of these in addition to other devices that may be sensitive to power draws. I think the capacitor does not hold enough charge, so when it's actually firing up a component, one of the switches, that the dew heater, when it starts, it's generating heat, so that's obviously going to pull a little bit more power than, say, like the camera would on its startup. So whenever it first clicked on, it was actually causing the camera power to actually fade out, and that would cause the camera to just drop briefly, just long enough that the Raspberry Pi thought it was offline. And the only thing that corrected that was rebooting the Raspberry Pi. And of course, if everything else was already on, no other issues. But since these processes kicked on at different times of the day, like the dew heater, you don't need it on at 9 o'clock at night. Usually you're going to need it on at 2 o'clock in the morning when the temperatures start dropping, where it starts generating the dew in the dome or on the top of the dome. The solution was to actually move the dew heater off to its own Wi-Fi power switch. Once I did that, I haven't had any other issues with the camera going unresponsive. So that was kind of maddening to troubleshoot, but eventually got resolved and we're good to go. Now I do have the camera installed. I went ahead and just put it in and got it all powered up and wired up. Of course, the power connection and the USB on this particular camera is directly on the bottom. And you can see I've got a dew ring up on top. And then, of course, that's my Mikey lens that connects to the camera itself. So this build is really pretty much done. The main things that you want to make sure that none of the wires are getting into the moving parts. So I've got all these wires tied up here to stay away from the fan. Actually, there is one more component we need to do. We need to put our screens in so that we do not have bugs and stuff getting allowing access up into there. We'll do that screen next, and then we'll do the same thing on this inner part of the case. Okay, so the templates that you can download, these are on the same website that you would have downloaded the software from. It will just say the SkyForge templates. So you can either cut this, if you have an X-Acto knife, you can just cut right around the edges of that and cut your template out like that. Or you just use a pair of scissors, and that's what I'm going to do here. I've got some scissors that I will just cut around the edge. It does not have to be perfect. Obviously, you don't want to go short on it because you don't want to leave any gaps on it, but you can definitely go a little bit wider and let it tuck up on the sides if you need to. It's not too bad with a pair of scissors. The straight edge ones that we're going to do that go on the actual tube, that one would probably be easier with the X-Acto, since you can just lay it flat on your foam board, not cut into your materials or to your desktop. My second grade teacher will be proud of me right now. I'm staying mostly inside the lines. All right, so that's show that. That's going to be what we'll use on the bottom. And of course on tube is basically two of these. So what we'll do is we'll find our long part on here and basically just kind of cut that down right along that edge. Unfortunately, I didn't cut this screen straight last time, so I can't go straight across on that. Probably come up just a little bit, start here, and basically just cut this out twice. And that will be the width that we need to cover the holes on the other one. So you get the idea on that. I'm not going to record cutting this. I'll just show you what we're going to do once we get them all done. So we have our screen stencils cut out. So we have the circle for the bottom that goes here. And let's pretend that I did this at the very beginning, because in hindsight, showing a video of me putting glue on the bottom that could actually drip inside to the fan and any other components would be a terrible lesson. So go ahead and do this part first. If you're following this video and you're going to build your own system like this, do this part first. This way you don't have to worry about dripping glue in there. So I'm going to go ahead and pause the video. I'll apply the glue carefully. I'll probably just keep it tilted like this so that I don't allow it to get into the fan. And we'll do the same thing for this on the neck of, it'll go on the inside neck of the tube itself. But yeah. Okay, so we've got the screen glued onto the bottom and didn't have too much drama with that. There's a couple spots that are raising up, but mainly around the edges is the main thing that we cared about, making sure that was adhered very well so it doesn't ever blow off. And then of course on the tube itself, inside the neck, you can see we've got the screen there. So this basically air is going to draw through these holes, down the bottom, out the bottom of this tube stack here, so, or the cradle stack here. So we'll push that off to the side. I do have the device powered up, as you can see by the flashing LED. These are on the Wi-Fi power switches. So now we're to the point where we need to program these. So we need to tell these switches what device is on which port, and this way when you're setting up your schedules for things to either be turned off, or if you ever need to restart something, you'll have that ability to do that from your phone. So I'm going to pause this video and I'm going to jump onto the screen recorder. Okay, so our devices are flashing they're in a pairing mode. If they've never been configured before, the actual power switches that we were looking at just a minute ago, they'll go into a pairing mode, which it flashes 3 times and then pauses. 1, 2, 3, pause. 1, 2, 3, pause. That's how you know it's in pairing mode. So we're now ready to go ahead and add them to our eWeLink app. And this is it's spelled EWELINK. And this is the app that controls your power switches, how you can program them, turn things on and off remotely, schedule off and on sequences. So we will go to the plus key, we'll hit add device. And then by default, it's going to try to connect it to your default network. If you do not want to connect it to your default network, I usually connect these on an IoT network just because I don't trust these Internet of Things devices. They're usually not very secure. Behind your firewall, everything's probably going to be fine, but you never know who wrote the firmware, things like that. So I usually put these things onto an IoT network, so it's completely VLANed off. But so anyway, these are going on the IoT network. So I'm just going to hit next. Okay, and on the screen, we have 2 devices listed here. We have one that has 2 dots. That's going to be our dual channel, and then one that has just a single slider, and that's a single channel. So let's go ahead and hit add, and we've told it that we want to put it onto the IoT network, so it already had that account and password. Okay, and it added it. You see a green check. We're going to hit next. Okay, and now we want to label this device so it doesn't just show up as device whatever on your screen. We're going to call this, since that was the dual, we'll call it the Wifi SkyCam Pi and camera. This way we know what this device is doing, because we're going to have another one that's going to be the dew heater. So we'll say okay to that, and we'll say done. Okay, so that one's good. Now we'll say done again. And now let's go ahead and add our other one on here. So we'll hit add device. Yeah, it's in programming mode. Sometimes if you wait too long, it may go into a standby mode. So we'll say next, searching for devices. And this actually, just as I did that, it went into the standby mode. So we are going to have to hold the button on it. Usually it's 6 to 8 seconds and it will go into the programming mode. Okay, there it went. So it sees it now. So this is the single channel power switch. So we'll add that one, and it takes just a little bit before it will get it completely connected to your network. And one thing if you do have trouble getting these things paired, this happens sometimes. I've seen people report this. If you have on your cell phone, disable your cellular service. Just have Wi-Fi only. Only if it gives you problems. Just disable your cellular service. Sometimes it has trouble navigating which network it wants to be on. It may try to go out over the internet to try to talk to this device, which is obviously incorrect. But that does happen on occasion. So if that ever happens, just turn off your cellular service. Just have your Wi-Fi only on. Okay, so we'll hit next. Now we want to edit this one, and we will change the name. Click the X. So this device only controls the dew heater. So we'll say okay, that done. Okay, and next, done. Okay, so you have these devices pre-programmed on your phone. Now, I'm going to just click this, and you're going to hear this relay click on. This is turning the dew heater on, so I'll just put it right up next to it. Okay, you hear that click, and that basically the red light turns on wherever it actually activates the power, so you know that particular device has power. And if you have a 2-channel, you've actually got 2 red LEDs. If you go into the dual channel, click that, you see how we have channel 1, channel 2. We just need to give these names, and you can do that by clicking up here. You'll go back into the name section. We'll click that, and then this is where you have channel 1 and channel 2, and we can change those names. And on this, now I know for a fact camera is on channel 1. Save that, and channel 2, we'll call that one the Raspberry Pi. So now whenever you're looking at the buttons, we'll move back out to the main interface. You see camera and you see Raspberry Pi. And then there's another view that you can do on here where you can change the layout. Let's see. Yeah, you can go to list view. And that's where you can see all your components directly inside the app without having to drill into it. So if you want to turn the heater off, you just click that. If you want to turn the camera on, it actually did turn the heater off. I don't know why it just didn't get a response from it, but it'll probably update itself in a second. All right, so that's it. Okay, now we are ready to discuss the programming of the thermostat. As thermostat, if you'll recall, we have it connected to our fan down here to where it will supply power to the fan once we hit our threshold on the thermostat itself. Now, if you're looking inside here, let's see, I don't know if this is going to come through with the LED flashing or not, but it's about 33.3 degrees, and we have our temperature threshold. I'll press this button, and it says 35 degrees. So 35 degrees is about 95 degrees Celsius. Now, it does not technically come on at 95 degrees. It has a 2-degree float before it actually turns on, and the float it's up. So it has to hit 37 degrees before the fan will actually turn on. And that just keeps it from cycling on and off constantly. If you set it at 95 degrees, once it went up, as soon as you hit 95 degrees again, it would shut off, and it would be a constant on-off process, which is not what you really want. So it waits until it hits 2 degrees above your threshold before it turns on, cools the system. Once it gets back down to your threshold, then it turns it off. So in order to change that, if I press this button, and we have currently at 35 degrees, these are plus and minus. So I can bring it up. I can say right now it's flashed at 35.0. Let me hit that button again, 35.0. If I hit that button, you see it's changing.
On the digital on the right, that's a 0.2, 0.3, so we're at 35.4 now, 35.6 or 35.5. You get the idea. Now we can bring those back down. I'll click that down. And back down to 35. So 95 degrees for me is a good threshold. That allows it to set the cooling temp that I want it to be at. Once it hits 37, which is around 98.6, the fan kicks on and it continues to run until we drop back down to that 95 degree set point that we had originally. So hopefully that makes sense. And the documentation on this device is not great. I kind of fumbled through it trying to figure out what different settings were, but finally got around to understanding that's what it was. And the 2 degree threshold is the default on there, and that can be adjusted. You can go to a different programming mode where you can say, I want it to be a 5 degree swing. So my threshold's 95, don't turn on until it hits 100 degrees or the equivalent in Celsius on that. And of course, where you put your thermostat, the sensor matters too. Obviously, you don't want to put it right next to the Pi, because if it's blowing its fan, it could put some hot air out too. Kind of put it up into an area that's not going to be near where any other warm air could be circulating at, so you don't get a on-off switch, like kind of a false positive on there. So hopefully that all made sense. And if it didn't, just leave a comment and I'll try to explain it better. So one of the best benefits of these wireless power devices are the ability to turn things off and on remotely. But of course, the greatest curse of them is these super bright LEDs. These things are so bright. I think they probably draw a watt themselves just based on how bright they are. So I've got one on each side. We've got the single controller and the dual controller. And to make matters worse, when you power up one of these power devices, like I'm gonna turn on switch number 2, you get a nice bright red LED along with that. So what we're going to do to fix that, and I'm going to turn on the light, we're going to just take some electrical tape and cover up those LEDs. And I've done this on all of my enclosures. It works great. It solves the problem. And to make sure we apply it into these little slots, I'm going to use a little plastic probe here. We'll make sure we cover. There's a second one right there. That's for the Pi. I don't want to turn that on and have to shut it down immediately. But yeah, we're just going to put a piece of electrical tape and tape it up against this wall, and then tape the remainder of it across this, and then we'll do the same thing. We'll just have a small piece that will cover that, and we'll do the same thing on the single controller that controls the PWM. And of course the PWM doesn't want to be left out, so when we turn it on, you'll see it puts a nice little bright LED right down there. So it wants to get into the party too. Big bright LED, but again, we'll just put a piece of tape over it. Problem solved.